Okay, this is one of the suggested problems. It's problem 66 from chapter 2. 66. A rock is thrown vertically upward at a speed of 12 meters per second. Exactly 1 second later, a ball is thrown up vertically along the same path with a speed of 18 meters per second. At what time will they strike each other? At what height will the collision occur? And then they're reversing the order, answer A and B, assuming that the order is reversed. The ball is thrown 1 second before the rock. Okay. So, as with many of these problems, I'm going to start by choosing a coordinate system, and traditional one is to choose 0 at ground level and plus as up. You can choose something else, doesn't really matter, but I'm going to be choosing this one. So we have a rock that's thrown with some, so V0 rock is 12 meters per second. This is positive because I throw it up, I chose up as positive. And then another 1 second later, we have a ball, V0 ball, is going to be 18 meters per second. And they collide. They collide. Now, do they really collide? Well, I think so, unless you're throwing this rock with so little velocity that it actually falls down to ground in 1 second. It will still be in the air, and the ball is just going to catch up with it or hit it on its way down. So if you draw this graphically, this might help understand us what's going on. For the rock, it would look like a parabola, and something like this. For the ball, it would look like a parabola like this. Okay, so with a higher slope, because it starts at a larger velocity, it starts like 1 second later, and they are going to collide. Not necessarily when the ball is still on its way up. It could be that they collide over here, but the picture is going to look something like this. Okay, so they are going to collide at some point. Now, how do we solve this problem? Okay, so the two things are colliding. That means that their positions are the same. So that's one clue that we can use, and we should use. Okay? So one thing that comes to my mind is that I write down the positions for these two objects, and I set them equal to each other, see if I can solve it. Okay, so let's try that. So X rock is going to be X0 rock plus V0 rock delta T plus 1/2 A, this is A rock, but doesn't really matter, delta T square. That's the same acceleration. So for the ball, which comes 1 second later, this is X0 ball plus V0 ball delta T plus 1/2 A ball delta T squared. And the accelerations are, of course, equal to each other. They are both the gravitational acceleration. Now, can we set these equal to each other? And they're asking for at what time will they strike? So can I solve for delta T? I seem to know pretty much everything here. I set these equal to each other. That kills two of my unknowns. And I'm going to be able to solve it for delta T. Now, please pause the video for a second and try to figure out whether you can actually solve the problem this way. Now, if you tried it that way, you'll immediately encounter a problem. Actually, this is something you could see without even attempting it. If you set these two equal to each other, these are both 0. They start at the ground level. These are both 1/2 G delta T squared. They'll cancel. So these are equal to each other. But this one is 12. This one is 18. You can't solve for it. 12 delta T is going to be equal to 18 delta T. There's something wrong with these equations. We have to go this. Well, one clue of what we did wrong is that we didn't use this at all. It should be there. Now this is delta T, but what is delta T? Delta T is the time elapsed until you reach, so this position is a function of time. So it is the time elapsed until I reach this position. It's starting from this position where my time was some T0 or something. So this is actually T minus T0. Okay? So T is time, that's what I read in my watch, but T0 is when this object started its motion. So it's more properly written as T0 rock. Okay? And now we can actually do this. This is going to be T minus T0 ball. And now these are not going to cancel, right? These two terms are not going to cancel, and you can't actually set these equal to each other. Now, this T0 ball can be written in terms of T0 rock, that it's the time when the ball started its motion. It's 1 second later. So T0 ball, I don't know, is T0 rock plus 1. Rock was being thrown, and then 1 second later, the ball has been thrown. You can actually set this to 0 and set this to 1. That's fine. You will be just setting the, when you start, press your chronometer or something. That is okay, but you don't have to. You can write it this way, and in fact, you can solve for delta t this way. You can solve for t minus T0 ball, for example, how much time has elapsed, that way, because you're going to have always terms in terms of that quantity. Okay? In that form, it is solvable. If you don't take that step, then you're not going to be able to solve this problem. And I'm not going to go through the algebra. You need to use the quadratic formula, which I trust everybody knows, that for quadratic formula is, if you have an equation like this, then the two roots of the equation is going to be minus b plus or minus e squared minus 4ac by 2a. Okay? And this gives you two answers. And you would expect perhaps two answers here, because if you go back to the graph I actually drew and then erased. So the rock was going like this, the ball was going like this. They could intersect again. Okay, so somewhere here or somewhere there. So you need to find where this t is going to be something positive. And if there are two positive roots, you should take the smaller one. Okay? It's possible maybe it goes like this and then comes back. It's again, but you're looking for the first collision. Okay? I'm not really sure what this would look like, but if you find two roots, you should just look at the physics and determine it that way. Certainly you should not take a negative time. It might be that these two curves intersect over here. But this is the way to approach this problem, that you write these positions, and indeed in a collision, the positions are equal, so you set these equal to each other, but you have to be careful what this delta t means. That delta t means t minus when you started the motion, so time that you read on your clock minus the time that you read on your clock when you started the motion, and they did not start the motion at the same point. They started 1 second apart. You have to take that into account. Now, this is the hard part of the problem. I'm not going to discuss the other parts too much. I'll just mention how you solve them. At what height will the collision occur? Well, you calculated some t or some delta t. You substitute them into maybe this one. I think that's easier. And you calculate the height. Just as a check, you can try to find whether they give the same answer by putting it into the other one. It should. Okay? But make sure that you're actually, subtracting off T0 for ball when you're doing the algebra for the second equation. And now for part C, you're going to switch this. So this is going to be a little bit different. Like this, like that. Okay? When you switch these, so the ball is thrown with a larger velocity, so it's going to spend more time like this. It could be that they never collide, that there is going to be some solution, some formal solution to our equation. So let's actually draw this. So you'll write pretty much the same equations, except this time, you replace 12 by 18, 18 by 12, and you're going to throw the ball first. The ball starts with a larger velocity, it reaches a larger maximum altitude, and then you throw the rock. Now, it could be that these curves do not intersect for this time interval during the flight off. So they will intersect over here, and I extend this over here, maybe, but that's not collision in air. Okay? The ball was in the air throughout this, and you have to check your answers. So I suspect one of them is going to be a negative t, and the other is going to be a t that's larger than the time of flight of the ball. But the physics is essentially the same. And why you get this nonsensical answers, this is that reason. Okay? If you plot position as a function of time for both objects, you see that their orbits never intersect. Okay? They're never at the same position at the same time during the time interval you're interested in. Okay? This is, I suspect, is the answer. I don't actually solve this in much detail, but this is the other trick of the problem, and this is why I suspect this is level 3, that delta T business and this one.